To embark on a course that studies calculus, you might be wondering a couple things like what is calculus and why do I need to study it other than, okay, it's in my, degree program or just, self-study, curiosity kind of motivation. Well, the answer to what calculus is, well, that's what you're going to learn throughout the this particular course. Why should you study calculus? Again, apart from it being possibly a requirement, and it's just the next thing you do after studying algebra and trigonometry. I'm just going to spend a few minutes giving you an idea, a few ideas actually, of what actually led to the discovery of calculus, right? And there are different ways these ideas can be formulated. I'm going to try to express them in as simple a way that, depending on your background, you should say, man, I never thought of that, but that question is an interesting one. So let's look at so I'm going to give you three reasons, right? And you can think of these as these are the fundamental problems. So these are fundamental problems of calculus, right? And what do I mean by that? Well, it means that these are the questions that some people had at some point that led them to discover this powerful tool, this area of math that is now ubiquitous in lots of areas of study, right? So here's the first one, right? And a couple of these require graphs. I'm going to sketch some graphs quickly, and these are graphs that should look familiar to you. So the first one is the tangent line problem. So the tangent line problem. And what do we mean by that? Well, let me sketch something over here. So I'm just gonna do some not so great axes, but here is our standard XY plane. And I'm just going to draw a graph. I'm not gonna write down any specific equation, just something very general. So y equals f of x, right? Now, I'm going to highlight or indicate on the graph 2 points, right? And I'm going to do these in blue. So I'm going to call this x value, just call it A. I'm going to call that one B. And then that means the corresponding point on the graph of the function. So that would have to have an ordered pair. And it would have an ordered pair with the x value A, and then the y value would be whatever number I get by plugging A into this function. And we know the notation for that. It is f of A. So I'm going to put that. So that's the ordered pair, right? But I'm keeping it very general because when you're describing something like this, you don't want it to be, I mean, you could use specific numbers, but part of this journey that you're going to take is to be more comfortable with abstraction, right? So things in general, it doesn't have to be specific, right? So similarly, this point on the graph would have an ordered pair of B comma f of B, like that. So in fact, let me go ahead and highlight these. So we have 2 points on the graph. We know the coordinates, and you might say, well, what if I connect these two? Actually, not just connect, but let's say there's a line that passes through these 2 points. Now, this line has a specific name. I'm not going to get into that, but just one thing, one property about this line I want us to be able to identify now, and it's its slope, right? And you know, we typically indicate the slope. So the slope of this line, I'll use the formula rise over run, right? And that's, you know, the change in y over the change in x. So I could take, I could use this as my first y value. So this would be f of b, and then minus f of a, the other y value. So this expression here is the rise, and then it will be divided by the run, b minus a. So like this, right? So really easy, we can compute this slope, right? And we know that for a line, right, the slope is a really important property. Okay, so that's pretty easy. But what if instead of giving you 2 points, an A and a B, what if I just gave you a point? Well, actually, let me do this. Let me redraw this so as not to get my graph too complicated. Or too messy, I should say. So let's say we have roughly the same function. Again, this is my x-axis, this is my y-axis. But now, what if I only give you 1 point? What if I give you just say a point here? And let's say I'm just going to call that C, right? So I don't want to use A and B since I've already used those there. But let's say this is another, like just any old point. And then what I'm going to do is draw a line that is, it's going to just touch the curve at that point. So it's not going to appear like it passes specifically through 2 points on the graph. But let's say it does something like this. Not perfect, but let's say it does that. Right? So all we have now is just 1 point. And if we follow the convention that we did up there, this would be the point C, comma, f of C in parentheses, right? And so we know that point, but the question is, what is its slope? Right? This red line, and I'll tell you what this one's called since it's actually that's how this problem got its name, if you will. This red line is called a tangent line. And the big question is, what is its slope? And because we only have one ordered pair that the line passes through, I can't use my nice slope formula from algebra, right? And it turns out that this is one of the first problems that people tried to solve that led to the discovery of calculus, right? This tangent line problem. Okay, so I'm not going to say much more about it. I just want to, you can think of this as like the teaser to say, man, okay, if you've never taken calculus before, you've never encountered this question before, you might be wondering, what is the solution? So that's like it's like a cliffhanger, like what's going to happen next? Well, stay tuned. So that's the first fundamental problem of calculus. What is the second? Well, I'll scroll down here so I can describe the second one. So number 2. And it turns out number 2, it sounds more like a physics problem. And this is the question of instantaneous velocity. Oh, I can't spell velocity. All right, so instantaneous velocity, like that, right? Now this one, I'll try to describe it with a picture as well, a little bit harder, but let's say you have not an X and a Y, but let's say you just have an X-axis. You have an X-axis, and then you have an object. somewhere along that x-axis. And it's moving either to the right, so that means either the x value is getting bigger, or it's moving to the left, meaning the x value is getting smaller. So it's just kind of going like this. So look at my little cursor. This is the object moving kind of back and forth, and sometimes it's going slowly, sometimes it's going quickly. And the basic question is this: at any instant, so at any instant, how fast is this object traveling? So how fast is, I'll scroll down some more, this object traveling, right? At any instant, right? So when it's right here, or right here, or right here, not like over an interval, right? So it's not like average, rate of change, right? We want the instantaneous rate of change. So how fast is it traveling at any given instant? Now, what's interesting is the solution to the tangent line problem is precisely the solution that we need to this problem, right? Which is, again, really interesting, and I just want to take a moment here to highlight this. From a purely mathematical standpoint, this problem here is a geometric problem, right? So it's something, it has to do with lines, lines and slope. You tend to use those ideas a lot in geometry, right? So this is a geometric problem, this tangent line problem. The instantaneous velocity, that's more, like I said, that's more like a physics problem, right? But it turns out there is a direct relationship between these two, and the relationship comes through calculus, right? And that's the power of this field of study. All right. So again, I'm not going to say too much more about it, but yes, instantaneous velocity is the second of these fundamental problems of calculus, right? People ask these questions, and in order to get an answer, they had to look to calculus. All right, what is the third one? The third fundamental problem, this one, again, is another geometric question. It's the area problem, right? How is the area problem defined? Well, again, it starts with another graph, another function. Oh, my axis there is broken. There we go. So let's say y x. Let me scroll down a little bit more. I have infinite scrolling, by the way, so I can go on and on forever, which, again, infinity actually is a very important concept in calculus. So again, lots of things to look forward to. So here is my y equals f of x, another similar shaped graph. They don't have to look like this. I just like to draw like wavy things. And this is how the area problem is defined. Just like my initial graph where I picked an A and a B, I'm going to pick another A and a B. I'm not going to color them now. I'm going to color something else, but not the labels. So we have an A and a B. And then what I'm going to do is I am actually going to define. And when we say that, it's like I am making something clear. Right? So I'm going to define a two-dimensional region. And what does that mean? Well, okay, so examples of two-dimensional regions that you'd be very familiar with are like rectangles, triangles, circles, ellipses. They when you draw them, they form a region, right? And so I'm going to form a slightly different type of region now, and this is how it's going to work. I'm going to start by kind of marking out more clearly that part of the x-axis. So between A and B, including the endpoints, right? And then I'm going to mark out another region, another line now that goes from A and it goes all the way up, and then it stops at the graph of our function. So it starts here and then it goes all the way up there. And I'll do the same thing for B, right? So start at B, go up here, stop at the graph. So far what I've drawn 3 line segments. And remember what a line segment is? You know, basically it starts at one point and it ends at another point, right? So it doesn't go off indefinitely in any direction. So start, stop, start, stop, start, stop, right? So I have those, but then to make it a region, I am going to again say, let's use this now to kind of form this region. So let me shade the region now so you can see it. And it's that part right there, right? So, you know, we might, again, in math, we love using symbols and we love defining things. So I'm just gonna call this region R. And again, so it's what's colored in red. But notice R it has 4 boundaries. It has those 3 line segments, but then the 4th boundary is a part of a curve. And based on what how this problem is named, the question is, so you notice all of these are fundamental questions. I'm asking questions that will be answered. And the question here that relates to this is, what is the area of this region R? Right? So again, in a physical sense, what would this really mean? So let's say you were to cut out a piece of, I don't know, cardboard or plywood or something in this specific shape, and then you wanted to paint it a certain color. The question is, how much paint would you need? Would you need half a gallon? Would you need 15 gallons? Well, I didn't give you any units here, so that would be a little bit hard to tell. But in general, that's how you can envision what the area of a 2-dimensional region is. Just take something flat, you know, let's say you were to trace this out on your wall, and then you want to paint that little region a slightly different color from the rest of your wall. How much paint would you need? Well, that's another it's a basic question that then leads to so many other possibilities, right? You know, so even though calculus started with these 3 questions, once you figure out the solution to these 3 questions, you're like, man, now I can answer more, and it just keeps going and going and going, right? So right, so that's basically what I wanted to present now, is just to give you a sense of what these problems are, and just to let you know that throughout your study of calculus, you will learn how to answer all of these and more. Right? So thank you for watching, and I'll see you at the next video.